Welcome back to Computer Lessons.
Today, we are stepping away from pure logic and entering the realm of brutal physics. You might think your computer is a machine that processes information, but from a strictly physical standpoint, it is actually a heater that happens to do math on the side. Every time you play a game, render a video, or even move your mouse, you are battling the fundamental laws of the universe. Heat is not just an annoying byproduct of computing, it is the ultimate limiting factor of performance. Today, we are going to learn why electricity generates heat, how thermodynamics dictate the speed of your processor, and the engineering marvels we use to move that heat away before it melts your silicon. To understand cooling, we first have to understand the source of the fire. Inside your CPU, billions of transistors are switching on and off billions of times per second. As electric current flows through these microscopic pathways, electrons collide with the atomic lattice of the conductive material. This phenomenon is known in physics as Joule heating, or resistive heating. Electrical energy is converted into kinetic energy within the atoms, causing them to vibrate more violently, which we perceive as a rise in temperature. There is no such thing as a perfectly efficient processor because the very act of resisting electron flow to control logic states inevitably creates waste energy. Manufacturers measure this output as TDP, or thermal design power, measured in watts. If a CPU has a TDP of 125 watts, it means the cooling system must be capable of dissipating 125 watts of heat continuously. If it fails to do so, the laws of thermodynamics take over, and the heat energy will accumulate in the chip until it reaches a critical failure point. To prevent self-destruction, modern chips use thermal throttling. When the sensor detects a dangerous temperature, usually around 100 degrees Celsius, the chip deliberately slows down its clock speed and reduces voltage. This is the computer saving its own life, but it comes at the cost of your frame rate and rendering times. Moving heat away from the die is a race against time, utilizing three modes of heat transfer: conduction, convection, and radiation. It starts with conduction, which is the transfer of heat between two objects in direct physical contact. The silicon die is topped with an IHS, or integrated heat spreader, usually made of nickel-plated copper. However, microscopic imperfections exist on both the surface of the CPU and the bottom of your cooler. If you placed metal directly on metal, there would be tiny air pockets trapped in between. Since air is a terrible conductor of heat, acting more like an insulator, these pockets would cause the CPU to overheat almost instantly. This is why we use thermal paste, or thermal interface material. This gray sludge is not a glue. It is a suspension of thermally conductive particles like zinc oxide or silver, designed specifically to fill those microscopic air gaps. Its sole purpose is to maximize the surface area contact between the heat source and the cooling solution, ensuring the most efficient conduction path possible. Once the heat moves from the chip to the cooler's base plate, we need to get it into the air. But air is not dense, so simply touching a hot metal block to the air isn't efficient enough. We need to maximize the surface area, and we do this using a heatsink. A heatsink consists of a stack of dozens of thin aluminum or copper fins. By slicing a block of metal into thin sheets, we exponentially increase the amount of metal that touches the air. A well-designed tower cooler might have the surface area of a small table, all folded up into a compact box inside your case. But how does heat get from the base plate to the top of those fins? We use heat pipes, which are arguably the most magical component in your PC. Inside these sealed copper tubes is a small amount of liquid, usually water or ammonia, held in a vacuum. Because the pressure inside the pipe is so low, the liquid boils at a very low temperature, often around 30 or 40 degrees Celsius. When the CPU heats up one end of the pipe, the liquid boils and turns into vapor. This vapor travels to the cooler end of the pipe near the fins, where it condenses back into a liquid, releasing its latent heat into the metal fins. A wick structure inside the pipe then uses capillary action to pull the liquid back down to the hot side, restarting the cycle. This phase change process moves heat thousands of times faster than solid copper alone could ever achieve. Now that the heat is spread across the fins, we need to remove it from the case using convection. Natural convection, where hot air rises, is too slow for high-performance computing. We use forced convection by attaching fans. Fans are rated by two metrics, CFM, or cubic feet per minute, and static pressure. CFM measures how much air the fan moves, while static pressure measures how hard the fan can push that air. For a dense heatsink or radiator, static pressure is more important because the fan needs to force air through the tight resistance of the metal fins. For high-end systems, air cooling sometimes isn't enough, so we turn to liquid cooling. Water has a much higher specific heat capacity than air, meaning it can absorb significantly more energy before its temperature rises. In an all-in-one liquid cooler, a pump pushes water directly over a copper cold plate on the CPU. The heated water travels through tubes to a radiator, which is essentially a giant heatsink. Fans on the radiator push the heat out of the case, and the cooled water loops back to the CPU. While it effectively moves the heat source to the edge of the case, remember that liquid cooling still relies on fans and air to ultimately dissipate the energy. Your entire computer case is an ecosystem of airflow. Positive pressure means you have more intake fans than exhaust, forcing air out of every crack and keeping dust out. Negative pressure means more exhaust than intake, which sucks air in through unfiltered gaps. Ideally, you want a directed airflow channel, cool air coming in from the front and bottom, picking up heat from components, and hot air exhausting from the rear and top. If you have dead zones where air doesn't move, components in those areas will cook in their own waste heat. For the extreme enthusiast, there are methods beyond standard thermodynamics. Sub-ambient cooling uses thermoelectric Peltier coolers to force temperatures below room temperature, but this creates condensation risks. And for world record overclocking, engineers use liquid nitrogen. At minus 196 degrees Celsius, nitrogen allows processors to run at voltages that would normally melt them instantly. However, this is temporary and dangerous, purely for the sake of pushing silicon to its absolute physical breaking point. Ultimately, the power of your computer is dictated by how well you can destroy energy. Every calculation creates heat, and your ability to manage that heat determines how fast you can calculate. It is a constant dance between electrical power and thermal dissipation. In the next episode, we will look at the box that holds all of this together. We are going to explore the case, airflow and form factors, and why the shape of your computer matters just as much as what is inside it.
Don't let your system overheat. Tell me in the comments, have you ever accidentally cooked a CPU because you forgot to apply thermal paste? If you found this explanation helpful, please hit the like button and subscribe to Computer Lessons. Don't forget to click the bell icon so you don't miss our next class. Thanks for watching and keep learning.